Now let's apply these concepts to a couple of problems. In the first problem, we are given a listing of 8 states which have a number of Fortune 500 companies headquartered in those states. So in a sample of 8, we have, between these 8 states, we have 283 companies headquartered. We'll use this information to answer a couple of questions. First, what's the probability that a company selected has its corporate headquarters in California? So again, our denominator is Fortune 500 companies. So we have 500 companies. Let C be the event that the company has headquarters in California. We have 53 such companies headquartered in California. Out of a sample of 500, this gives us 0.106. Let B be the event that the company selected has headquarters in California, New York, or Texas. In this case, we will now add up the probabilities. So let's first find the probability that the company has a headquarters in New York. In New York, we have 50 companies. Our sample is 500. So this is 0.1. In Texas, we have 52 companies out of 500, and this number is 0.104. So to find the event that our companies are headquartered in any of those 4 states, we will add the probability of headquarters being in California plus probability of headquarters being in New York plus probability of headquarters being in Texas, which is 0.106 plus 0.1 plus 0.104, and this gives us 0.31. So probability that the headquarters are in any of these 3 states is 0.31. If we wanted to find the probability that a company is headquartered in any one of those states, we would do our number, which is 283, divided by 500. So again, probabilities are just looking at the number of ways in which an event can occur divided by the total number of events possible. This problem is a bit more interesting because we are now expanding our vocabulary to introduce 3 new terms. One is complement of an event, then union of 2 events, and intersection of 2 events. So here we have a sample space with 5 equally likely experiments. Again, we are saying that each of these can happen with the probability 1/5. So this would be our classic probability. Let A be the experiment where either we have event 1 or event 2. Let B be the set where we have event 3 or event 4, and C be the set where we have event 2, 3, or 5. So based on these, we will answer some questions. What is the probability of A occurring? And again, B and C will work like that. So probability of A occurring, A is again our E1 or E2. So we have 2 possibilities out of a possible of 5, 0.4. And then similarly, we can see that B has 2 out of 5. So we'll have B as 0.4. And then probability of C, in C we have 3 possible events out of a total of 5. So we have 0.6. Now you might wonder, if we add up 0.4, 0.4, and 0.6, we're getting a number more than 100 or 100% or 1, but we had seen that they all add up to 1. Well, there's an idea of intersection because there is a common event which some of these sets share. So we'll look at that in just a little bit. So first, look at PA union B. Union is the possibility of event given by the union of A or B happening. So this is the idea of OR. Union is OR. So A or B happens. So let's first define what A or B means. So A union B is the set, again, A has E1 or E2, and B has E3 or E4. So here we have 4 possibilities out of a total of 5. So the probability of A union B is 0.8. And as we notice that A and B have no elements or no events in common, so we say that they are mutually exclusive. So mutually exclusive events are events which share nothing in common. The third concept is of complement. Complement of a set is a set which has all events other than the events described in that set happen. So our A was our set of E1 and E2. So A complement will be everything but E1 and E2, which would be E3, E4, and E5. So the probability of A complement, we have 3 possibilities out of 5. So we have 0.6. And then same would be the idea with C complement, etc. D is now looking at the intersection of union of A and B complement. So let's first define this event. In D, A union B complement, again, A is set of E1, E2, B is set of E3 and E4. So B complement is the set of everything except E3 and E4. Right? So let me kind of highlight that. B complement is the set of E1, E2, and E5. So if we are creating a union of A and B complement, A has E1 and E2. B complement includes E1 and E2, which has already happened in A. So it's A or B. So the only event that has not occurred in A then is E5. So this implies that the probability of A union B complement, again, is 3 over 5, which is 0.6. Let's look at B union C. B union C, again, would be B is E3, E4. C is E2, E3, E5. So the only thing common is E3, so we ignore E3. It will be a set of E3, E4, E5, which again is 3 out of 5 events, so the probability would have been 0.6. Or P of B union C equals 0.6. The final problem we did in part 1 of this video lecture, which involved trying to find probability of A, B, and C, which were defined among 5 possible events, was an application of the addition rule, which is what we'll now formalize. So the addition rule says that the probability of union of 2 events A and B is given by the probability of A plus the probability of B. And then we do not want to double count, so minus the probability of A intersection B. The applications we did in the previous problem in the last video were applying this rule. The second important rule is the multiplication rule. And the multiplication rule says that the probability of A intersection B, that is A and B happening together, is given by the conditional probability of A given B times the probability of B. So what this means is that first event B has occurred, and then what is the probability that A will occur given that event B has occurred? A more common form in which we see this rule is the conditional probability formula, which says that probability of A, and this line means conditional on. So the previous event that has happened is B. So this is asking what is the probability of A conditional on B? And that's given by the probability of A intersection B divided by the probability of B. So B is what is also called the marginal probability. It is probability of event B happening. And given that B has happened, what is the probability of A is what this formula is trying to get to. This also leads to the definition of independent events. When are events A and B independent? Events A and B are independent when the occurrence of B has no bearing on A happening. So A and B will happen just on their own. So for example, what is the outcome of tossing a coin and rolling a die? So here, tossing a coin's outcome is independent of the outcome we get from rolling a dice. So more formally, the independent event is described as the probability of A conditional B is same as probability of A. So here, B's occurrence has no impact on A's occurrence. And if A is independent of B, this implies B is independent of A. So we can also add that probability that B is independent of A is same as probability of B. So this kind of also takes a new application on the conditional probability times the intersection rule. So if P A intersection B is given as PA conditional on B times PB, if A and B are independent, then we can say that P of A intersection B is, because now this is same as just PA, is probability of A times the probability of B. Again, this is the independence law. It is derived from the multiplication rule. So these two rules, the addition and multiplication rule, are really important in calculating probability of various events. So let's apply this to a formula. Let's say that we have a local restaurant and knows that the probability that the customer will order pizza, let's this be the event Z, is 0.87. And restaurant also knows that the probability that the customer will order salad, let's call that event S, is 0.32 or 32%. We also know that, now notice the language, of those who order pizza, 55% of them also order a salad. So of those who order a pizza, 55% also order a salad. So this is giving us the probability of salad conditional on pizza. So this equals 0.55. And then we know that probability of Z by itself, or people ordering pizza, is 0.87. And probability of salad, people order salad, is 0.32. So the question says that we randomly choose a person, find the probability that the person is buying a pizza and a salad. So again, we can apply our multiplication rule. Probability of Z intersection S is probability of someone having bought a pizza, and given that they have bought the pizza, what is the probability of them buying the salad? So PZ times PS conditional on Z. And that's given as 0.87 for PZ times 0.55 for the conditional probability of S given Z. And running this in Excel or in a calculator, we get 0.4785. So the probability of a person buying pizza and salad, this PZ intersection S, is given by 0.4785. The next question is, are S and Z independent? So S and Z would be independent if the probability of a person buying salad would only depend on that and not depend on what the person did before they bought the salad. So here, that is not the case. So these events are not independent, they're dependent events. Let's look at another question. Again, it's more straightforward. Here we are given probability of event A is 0.5, probability of event B is 0.6, and probability of A intersection B is 0.4. So now we have to find the conditional probability of A conditional on B. So conditional probability of probability A conditional on B would be probability of A intersection B divided by the probability of B. And B is the marginal probability in this case. B has happened first. So our A intersection B is 0.4 and probability of B is 0.6. So this is 2/3 or 0.66. On the other hand, probability of B conditional on A is probability of A intersection B divided by probability of A. A intersection B is 0.4 and probability of A is 0.5. So the answer is 0.8. And are A and B independent? Again, they're not independent because probability of A is not the same as probability of A conditional on B. So here probability of A was 0.5 and probability of A conditional on B is 0.66. So hopefully this clarifies the idea of the multiplication rule in action, or the conditional probability formula, because this is the base of how Bayes' theorem will be brought about. This idea of marginal probabilities can be gauged by this table as well. So let's say there was a survey done of adults from 18 to 34 years of age saying, do you still live with your family? And we have the responses and raw data given by this first table. So the rows tell us for male whether they live with their family, yes or no. And then this is the total number of male respondents. The second column tells us the females, yes and no. And then if we look at the columns, we get of those who said yes, how many were male, how many were female, and then this is the total number. So we can see that the rows will add up to the column number. So the summation of this column across the rows is the number of people who said yes. The sum of the second column across the rows is number of people who said no. And if we add the columns for each row, we get total number of male and female respondents. So these are the marginal totals. To calculate probability, we often divide all these numbers by our raw or grand total, which is 500. So the next table is essentially all of these numbers divided by 500. So this table is called the marginal probabilities, or the relative probability table. The marginal probabilities are the totals that we get for each either column or addition of various rows. So what is the probability of living with family given you are 18 to 34 years old male? So given male, so here male is our denominator, male is the event that happens first, and then we find the probability given male. So in this case, we will write the required probability as probability of response yes, conditional on male. And we can use this table to easily calculate that. This is the intersection of male and yes, and male is given by this marginal probability. So this is given by, again, if we want to be more formal, we can write y intersection m and probability of m. And again, we said things along the columns are the marginal probabilities. This is given by 0.212 divided by 0.494. And this equals 0.29. So the probability that someone is staying with their family, given their male, is given by that. And then probability someone, so probability of an 18 to 34-year-old living in the United States with family, it just asks for probability of yes. So here we would look at the marginal probability, and yes is 0.396. So this is, we can just read this of our table. Again, so this shows the difference between conditional probability and the marginal probability. So probability of someone living in the family is just the sum of this column, which is 0.396. But when you look at the marginal or the conditional probability, then we look at the intersection and we divide it by the requisite marginal probability.